Hello, and welcome to Acoustics Derivations. In this video, we will be deriving the D'Alembert solution to the lossless 1D wave equation for a 1D system with no boundaries, for example, an infinite string. So if you're familiar with the wave equation, you know the general solution of the wave equation is given by this. U is a function of f, which is of itself a function of x minus ct, plus g x plus ct. So to derive the D'Alembert solution, we assume that we're given two initial conditions. If you're familiar with differential equations, this is a second order partial differential equation, and so you need two boundary conditions to be able to solve. And so our boundary conditions, or in this case, our initial conditions, are that at time t equals 0, at some point x, the displacement, if you were talking about a string, is equal to p of x. And we know that then we can write that as f of x plus g of x. And our second initial condition is that the time derivative of u evaluated at t equals 0 is equal to some q of x. Now, I will label this first initial condition star, as we will need it later. So first, let's work with the second initial condition. The time derivative of u at t equals 0 is equal to q of x. So let's do it. We see that q of x is equal to, taking the derivative of our general solution. Let me box this in so I don't erase it later. We see that it is negative c times f of x minus ct, and that f should be prime, where the prime denotes a derivative with respect to the argument, plus c times g plus ct. And now, if you remember our initial condition, it needs to be evaluated at, put a parentheses here so it's clear, at t equals 0. So simply everywhere we see a t, we put a 0, and we see that this is negative c, that g should be a prime, negative c times f prime of x plus c times g prime of x. And that's what q of x is. Okay, lovely. But that's not quite enough yet. We want to be able to equate equations, this equation star, with q of x. And the way we're going to do that is through f and g of x. But if you look down here in equation double star, we have an f prime of x and a g prime of x. Well, how about we integrate a double star? And we're going to integrate between some arbitrary point x some arbitrary point x naught and x. Why some arbitrary point x naught? Well, some textbooks integrate from 0 to x, but x naught is more general because you can set x naught to be 0 or something else. And when we integrate, we're going to integrate with respect to y, because it is quote unquote bad calculus to integrate, or to have your integration variable also be the variable you're going to substitute in with the bounds. And so we just let y be a dummy variable as a stand-in for x while we integrate between x naught and x. So when we integrate double star, we have x naught, the integral from x naught to x of q of y, it's a terrible q of y dy is equal to negative c f of x plus c times g of x. But because we're integrating from x naught to x, we also have to have we also have to plug in x naught everywhere. So it's going to be minus negative c f of x naught plus c of g of x naught. And once again, we want to be able to compare the first initial condition which has an f of x and a g of x, and we have a c times an f of x and a c times a g of x. So just to make our lives a little bit easier, we're going to divide the whole equation by c. We have 1 over c times x naught x q of y dy is equal to negative f of x plus g of x minus negative f of x naught plus g of x naught. Lovely. And for convenience, as we move forward, let's denote this whole quantity k naught. We'll see that this eventually goes away, so we can make it a little bit easier on ourselves. We don't have to write all of that over and over and over again. And I will call this triple star. Okay, lovely. So now what we want to do is we want to rearrange, and I'll write this on this side of the board. We want to rearrange both star and triple star to solve for f of x and g of x respectively. So we start with equation star, and we write that as f of x is equal to p of x minus g of x. Similarly, we write g of x is equal to p of x minus f of x, right? Simple substitution. And the one that's a little bit more complicated, but really not that complicated at all, hope I don't make any mistakes now that I've said that, is triple star. So first we can solve for f of x. We can see that f of x is equal to g of x by moving it to the other side, minus k naught minus 1 over c times the integral of x naught to x q of y dy. Similarly, for g of x, we have g of x is equal to f of x, but now we have plus k naught plus 1 over c times the integral of x naught to x q of y dy. Okay, lovely. So now I will erase this over here on the left. So now, what we're going to do is we're going to set the equivalent relations in star and triple star equal to each other. So setting f of x equal to f of x because it is, and then their relations or their equations are also then equal to each other. We obtain p of x minus g of x is equal to g of x minus k naught minus 1 over c times the integral from x naught to x q of y dy. Okay, so then we obtain negative 2 times g of x is equal to negative p of x minus k naught minus 1 over c times this integral. And finally, we divide everything by negative 2, and we obtain this expression for g of x. And now let's do the same thing by setting the g of x equations equal to each other. We have p of x minus f of x is equal to f of x plus k naught plus the integral of x naught to x of q of y dy, and remember that integral is divided by c. So once again, let's rearrange and solve for f of x. And I realized I've made a mistake up here. Hope you weren't screaming at your computer screen. I forgot to carry the division. So this should be a plus and this should be a plus because it's divided by negative 2, not just 2. So my apologies. So let's divide by negative 2, and this time not forgetting the negative as we did above. All right, lovely. So I'm going to erase this on the side now that we've used them. They're not that important to us anymore. So we're almost done, but we need to note two things here. First of all, we have these expressions for g of x and f of x, but that really means g of x at time t equals 0 and f of x at time t equals 0. Because remember, f and g depend on both x and t. So what we can do is then substitute in x minus ct for x in the f of x equation, and x plus ct into x in the g of x equation. So that allows us to move forward in time. So let's make that substitution. X minus ct into x gives us in f of x, I should write in f of x, so it's a little bit more clear. We find that f of x minus ct is equal to 1/2 times p of x minus ct minus k naught minus 1 over c times x naught x minus ct q of y dy. And similarly, we want to do x plus ct in for x in g of x. So we have g of x plus ct is equal to 1/2 times p of x plus ct minus, plus k naught plus 1 over c times the integral of x naught to x plus ct q of y dy. Okay, fantastic. So now I can erase here on the side. Now we're just about done. But we note that the general solution to the wave equation is u of f of x minus ct plus g of x plus ct. And so we've just solved for f of x minus ct and g of x plus ct. So let's plug them in. So u of x and t is equal to 1/2 times p of x minus ct plus p of x plus ct minus k naught plus k naught, and these will cancel. As I said before, they're going to cancel. Minus 1 over c times x naught x minus ct q of y dy plus 1 over c x naught x plus ct q of y dy. Okay, we're almost there, but now we need to note one final step, one final thing before we have our final solution. And let me move this up just a little bit here. Ooh, 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 ooh. Okay, move it up just a little. There we go. Okay, it shrunk a little bit, but hopefully you can still read that. We need to note that an integral, when you have a negative integral, that is the same as inverting the bounds on the integral. Okay. Think back to your calculus days. And another thing about integrals is if you have, and this is once again, think back to your calculus days, two integrals being added together about, or with the middle bound, so the upper bound of the first integral and the lower bound of the second integral are the same, you can actually combine this into one integral. Usually you might see this going the opposite direction, taking one integral and dividing it into two for various mathematical reasons, but you can in fact go back the other direction. And we will employ that fact here. Then, all we must do is rewrite these two integrals as one, and we will obtain the D'Alembert solution. So u of x and t is equal to 1/2, and then brackets, p x minus ct plus p x plus ct, plus 1 over c times the integral from x minus ct to x plus ct of q of y dy. All right, there you go. That's the D'Alembert solution to the lossless 1D wave equation for a 1D system with no boundaries. Once again, that's similar to, or like an example of that would be an infinite string. Now, just final comments here. Note that if Q is equal to 0, that is if the velocity du dt at time 0 is equal to 0, the forward and backward traveling waves have the same shape as the initial disturbance, but they have half the magnitude because it's a 1/2. Okay? All right. Thank you very much.